Today we've got a couple of, we go over adaptive management some more because it's really important for what we do, and there's a ton of linguistic uncertainty around it. And no. So, as we talked about last time, there's at least in my opinion, there's a huge amount of uncertainty as to what adaptive management is. You go into Google. What's that?
I couldn't get to the class when I did the drop down.
Oh, so the window's too big. I've got it on the index right now. So if you go to course home, it's listed right there, so you can get to it right from the home page. So we talked about all these fuzzy graphs and circles and whatnot, and every time I see an adaptive management talk in a meeting or something like that, everybody's got some iteration of a graph that looks like that. And I always struggle with it because I never see it going anywhere besides a pretty picture. And what we did last class was we went and formally did this loop using a process where we could formalize learning, we could quantify it, we could make predictions, make decisions. And the key was that we reduce structural uncertainty so that we can adjust our decisions to match what we know about the system. So, hopefully, if you come out of anything out of this class, it's a good idea of how that stuff works. So today, I'm going to go into a little bit more. Everybody see that? Yeah. So there's a couple of background readings I put up here. One is an intro to stochastic dynamic programming. If anybody gets a real interest in terms of harvest management, trying to come up with the best decision that over a long-term sustainable window, SDP is really the way to go. So there's a nice paper by Marscott, came out 2 years ago, and they do a nice step through on what SDP is, how it's used. It'll make your head hurt. I won't deny that. But it has a nice figure where they show how the backwards recursion of trying to iterate and find optimal policies. Now, I'm not going to make you guys do that. I'm going to actually show you guys the software in R that'll do it for you. So, now we spent a long time talking about a pig model. We've talked a lot about fish stuff because I have an inherent bias towards that. Left the duck guys out of the loop, so today we're going to talk about ducks. And so, there's a couple of papers posted up here. We've got the original Conroy, Miller, and Hines. The big mamma jamma here, which is about 68 pages of black duck adaptive management. And it'll go over adaptive management and how they were using it to develop the adaptive harvest management plan for black ducks. So, which we'll be discussing a little bit today. Now, I'm going to caveat that I'm not a black duck expert by any means. I'm going to be mostly going over some of the broad stuff, the objectives and those sorts of things. And then, and we'll be talking about how we apply SDP to exploitation of ducks. So this is the original paper by Anderson, did the additive compensatory of adults and juveniles. So we'll touch on that a little bit today. So those are there for you guys to take a peek at. Got the script. You guys are going to play along today. We're going to be using MDP Toolbox, which is the program that we can use to do policy iterations. So we can do that SDP process in R. MSNs for doing some truncated distribution stuff. FitDist Plus, if we get into the bottom of the class today, we're going to be talking about some of the expert elicitation. So I had you guys do a expert elicitation process last time. probably won't get to that today, but we'll follow up with it on Wednesday. And HMISC is a package that has some weighted values, functions for calculated weighted means and variances. Okay. So we've talked about the importance of monitoring in adaptive management. And it basically gives us 3 steps. It gives us an idea of where we are, so it sets up what your current system state is, because a lot of times you're making decisions that depend on the current system state. After you implement the management alternative, it provides information on what changes, where do we end up, and then lastly, it provides information on system dynamics that we can use to reduce uncertainty. So this is where the learning occurs. We can come up with these alternative hypotheses of how a system works. So keep going back to that additive versus compensatory mortality. Alternatively, you can come up with a bunch of different hypotheses for how habitat may affect something. So it's critically important in terms of adaptive resource management. A lot of times in state agencies, different programs, we're already doing some form of monitoring. It's just a matter of trying to get those monitoring programs to talk to the management programs. And so you have a situation where monitoring and models are tightly coupled. All right. Now this tends to be a little bit of an issue because a lot of folks get into the field that not because they want to model, because they want to go out and count ducks or count fish and do that sort of stuff. But as a process of that, we start to make these mental models where we're starting to make predictions that are guiding our management. And all we're doing here is taking that implicit model and making it explicit so that we can start to use it, probe it, and evaluate it in a formal way. Now, one of the keys to this is making sure that what we've got going on in our mental model, we can get it down on paper, that what we're predicting matches what we're monitoring. Okay? So if you're trying to manage duck populations, you have to measure duck populations. You have to estimate how big those populations are. If you're doing stuff with fish, you got to estimate how many fish are out there, which is a big challenge when you're dealing with lots and lots of fish. And so sometimes you get creative in what you do, but the gist is that you've got to match what you're doing in terms of your prediction. So taking your mental model, putting it down on paper, making it explicit. You're predicting abundances and using abundances as a value as part of your objectives. Then you need to monitor with abundance. So if you're thinking about objectives that include species richness, you got to go out and collect the number of species. We've got distribution occupancy. You got to go out and measure or estimate the proportion of the areas occupied. Think about area burned. You go out and collect the area burned. So there has to be a match between what you're doing in terms of your predictions and what you're monitoring in terms of what you're measuring and the scale of it. So that leads to issues when you start to use things like raw counts. So I think I started talking about this early on when they talked about the idea of statistical machismo and occupancy stuff that wasn't really needed. But part that was missing from that argument was the fact that you need to have unbiased data to make decisions in terms of doing management. And so if you actually go and do the value of information on biased things like catch effort data, population indices, there's actually negative value to collecting that data in terms of making a decision in some cases. So we can demonstrate that using the value of information or value of imperfect information and find that you actually sometimes make the wrong decision when you have biased data. Okay. So what do we need to monitor? A lot of cases we're monitoring the things that we're managing. So we're talking about ducks, talking about fish. We might be monitoring dynamic rates. Sometimes you have cases where you can't monitor everything. You can go out and monitor abundance, you might be able to monitor survival, you might be able to do breeding surveys, something like that. But at some point something might have to give because right now a lot of state agencies are facing budget shortfalls, budget cuts. So what do you scrap? What's important? And so at least using a sensitivity analysis, if you have a decision process put together, you can figure out what might be important and what won't be. But in terms of adaptive management, we want to start to measure the key drivers outcomes, so things that are pretty sensitive. Especially need to look at values needed to estimate the expected outcome after a decision. So in that red horse example, we were talking about estimating the number of red horses that were out there. And we also need to keep track of things because we can have unexplained outcomes. And this was, I think Marley was talking about this last time, where what happens if what you think is going on, your decisions aren't working, okay? So monitoring other elements of the system are important to start to ferret out what's going on in terms of the unexpected or unanticipated outcomes. And so the key here is that it's largely dependent on resources. So you usually got finite resources, so you need to be strategic in the way that you allocate those to do the monitoring effort. And so using some sort of sensitivity analysis to evaluate the uncertainty, expected value of information, we can start to look at what's important. And so a lot of cases, we have to be able to figure out what the outcomes are, and that's largely one of the most important ones. Okay, so you're using something like population size, distribution, harvest to make your decision, then you absolutely for sure have to monitor that so you can make some sort of decision and learn over time. Some of the other stuff you might or might not be able to get away with monitoring that. So if those three were part of the utility, so we got population size, distribution, or harvest. Some of the ancillary stuff you can think about monitoring be habitat. A lot of cases we're going to make decisions that are dependent on the amount of habitat out there. So we have these state-dependent decisions that might depend on whether or not you got a whole lot of different habitat, whether that habitat's available, things like annual temperature and precipitation. So before, if we collect these data, we can throw them in the model, we can use them to make state-dependent decisions, start to account for environmental variability, and the key is that we're trying to be useful in terms of explaining some of those unanticipated outcomes. All right. So the process, while it seems rigid and rigorous, is flexible. We talked about this a little bit, but we've got this what's called single and double loop learning in adaptive management, where we've got that single loop that we iterate over each year to figure out what the ideal management action is, optimal management action is, go implement it, go monitor, see how that monitoring maps back to what our expected value was, so we can start to learn about competing hypotheses. And we have to do that 2, 3, 4, 5 years, depends on the decision-making context, but at some point we can jump out. We can jump out, reassess the problem, reassess the objectives, reframe the situation, potentially put new alternative hypotheses into the mix, give them weights, and carry on with the process. Now, the big key here is you got to be able to stay in that single loop long enough to learn, okay? Because if you jump out after 1 year or 2 years, you might be jumping out and just visualizing what's going on with environmental variability rather than what's going on in terms of the long-term dynamics of the process. And so environmental variability can kind of obscure what might be going on, and so you have to be willing to kind of commit to this for a couple, 5, 6 years, depending on the process. I mean, a lot of cases, some of these processes can play out within a year. So an example of that was we started to look at spring Chinook transport in the Willamette Valley. So each week or so, they were transporting 50, 100, 200 Chinook upstream. So we actually had a weekly time step that we could start to do management actions in terms of, do they aerate the tank? Do they not aerate the tank? Do they get old Rusty and not let him drive because he's a maniac? And those sorts of things. So you got to be staying there long enough to learn. Now, the nice thing about that Willamette model was that basically after a season, you could jump out. Corps of Engineers had a working group. And they'd meet in the springtime, kind of assess where they were going, and that served as that double loop for that situation. So, take home here is that adaptive management is a special case of structured decision making because we're looking at sequential dynamic decision making. And we're incorporating these alternative hypotheses of system dynamics and using the monitoring to feed back into that iterative process to reduce uncertainty. And that's, I think, where the key is and a lot of misunderstanding of what adaptive management is. Now, keep in mind that what I am espousing here is a very strong flavor of decision theoretic side of the adaptive management coin. The other side is the experimental resilience side, which people are very into doing collaborative decision making, getting all the stakeholders involved, and sometimes we probably should what we call kumbaya adaptive management because it seems like there's a lot of hand holding and stuff like that. But it has its place and it's good. My preference is for the decision theoretic side because it seems like you get the ball rolling and you're making decisions, whereas in collaborative adaptive management, it seems like you can be out 3, 4, 5 years before you actually make a decision. So, one of the key differences between decision theoretic and the experimental resilience school is that the decision theoretic makes stakeholders get their objectives out really early in the process, whereas in the experimental resilience, they're going to start to sort of pull those out. They're not as a priority as they are in the decision theoretic context. So, we've got the single loop. Begins after we come up through our PERAC process. We get our initial structured decision-making process complete. We come up with our objectives, our decision network, build some decision models. We start learning within that single loop. Okay? And all this happens relatively frequently. So maybe on a weekly, daily, even yearly time scale. Now, as decision makers go over time, they may find that their current set of models is inadequate, so we start to identify that, all right, we came up with these models thinking that low variability was what's driving the system and predation. Well, maybe it's not that. Maybe it's habitat. It might be habitat limitation, so they can throw together a habitat limitation model and add that to the mix. Maybe at some point they think that flow variability just there's no evidence for it, they can throw it out. Ultimately, it's up to the decision maker. And when that happens in the double learning, the double loop process. They go through, reassess the management actions, the alternatives, and they can revise, reassess, that sort of thing. Now, there's no hard and fast rule on when you jump in and out of the single versus the double. The only key thing is that you want to stay in the single loop long enough that you can learn something. And so in that example from Robust Red Horse, we saw a lot of bouncing around in the different models. So after 5 years, it might make sense to jump out because you're not really seeing strong evidence for one or the other. So we saw this last time. We've got the single loop that represents basically that first adaptive management loop, and then you jump out and you can revise your process. All right. So it is flexible. I mean, a lot of people will say that it's not flexible, but we found it to be incredibly flexible. That we can take different models, take different predictions, do stuff with them. We're starting to modify them to fit decision situations. We're incorporating decisions, monitoring feedback, and all these can potentially occur at different intervals. So, for example, start to use controlled burns to manage vegetation. You may only have to revisit an area every 3 to 5 years or something like that. But you may have to monitor that vegetation annually. And then other situations you may have to visit frequently or infrequently do a slow system response. So if you think about river dynamics, all of a sudden you change some flow, it may take a couple years for a river to respond to that. Good example of that in the context of a legislative mandate is when you think about FERC relicensing for dam. Dams come up every about 20, 50 years or so. They come up for relicensing. And that might be a time where you can jump out if you're doing an adaptive management process. Use that to jump out, reassess what you're doing, and jump back in. Or if that ends up being your evaluation, you jump out, do it, but then you're looking at another 20 to 50 years before you get another data point. So that's kind of an issue. So that's where that idea of spatial replication works, that potentially if you're doing adaptive management on a dam, hydro system, you come out in 20 years, get a bunch of data, goes back into being a dam, the decision might be to remove the dam or not, then you're looking at 20, 50 years down the road. So that's a career for a natural resource biologist. So what you can do in that situation is start to think about, if we're going to do this on this dam, this one's coming up in 2 years, so we can try to use that same process to learn by using spatial replication instead of temporal replication on a single dam. So this is the idea of adding spatial feedback, where we've got decisions made on one project, the hydropower, and monitoring is conducted to resolve uncertainty about system dynamics, update beliefs. We've already gone through how we do that, and use that model to identify the optimal decisions at different locations. Now, this is this idea of sequential dynamic decision making in space. So we're making decisions over time, sequential, and we want them to be dynamic. We want them to change with the conditions depending on what's going on in the system. So, to make things even more confusing, we've got two types of adaptive management beyond this experimental decision theoretic camp. Regardless of whether you're experimental resilience or decision theoretic, both programs have what can be active or passive adaptive management. Now, the process is exactly the same for whether you're doing passive or active adaptive management. I've shown you guys how you can actually implement an adaptive management program. The process is exactly the same. Okay? We've got alternative models. We're using those to identify the optimal decision. We're using monitoring data to improve our understanding system by updating those posterior beliefs. In passive adaptive resource management, the key here is that we're making decisions as if current uncertainty about system dynamics will not change. So what that means is that the weights that I calculate for my posterior do not change over, say, a 20-year period when I'm starting to make a policy decision that iterates over time. Okay? But that may not be the case. We may think that the flow variability model versus the predation model, the weights of those may flip over time, and us assuming that they stay the same isn't really a good idea. That's where active adaptive management comes in, and it takes into account how we can reduce uncertainty, and that can affect the long-term gain. So that builds in to your optimization. What are the decisions that are going to maximize your learning over time? And it's incredibly difficult to do. And it's usually, there's only a handful, maybe 2 or 3 cases that I know that have actually successfully done it. There's the horseshoe crab red knots on Chesapeake Bay, the adaptive co-management that Connor McGowan did out of Auburn. And there might be one other. This was probably the best case where they actually used active adaptive management. Most of the time we end up doing passive adaptive management because it's a shit ton easier. And managers like it because you're working with management actions and you're not trying to front load learning. So in this case, you're just trying to come up with the best management action. That's what managers want. Learning becomes secondary. We as scientists want to learn stuff. We probably prefer active management or adaptive management, but it is incredibly difficult to do. And the difference really comes into, you've got this relatively simple adaptive management for passive. The active side, it becomes really computationally intensive. And so, unless you got a PhD in operations research, math, or optimization or something like that, it's really a challenge. And so, most people shy away from it, and it doesn't really matter in a lot of cases because managers want to make good decisions. They're not necessarily as interested in front-loading learning. So we're choosing decisions as if uncertainty will not change. In this case, we're trying to choose the decisions so that they form good contrasts that we can learn over time. So if you think about probing the system as trying to pick that decision that's really going to hit that system hard and provide a good contrast that we can learn from. All right, we're getting information gained through monitoring and incorporated, but we're not necessarily doing that in a planned way. And in this case, in adaptive management, you start to probe the system. And probing, in this case, is taking a management action or taking a big stick and hitting the system to see how it responds. And we can do it in a situation where uncertainty is incredibly high, or in cases where management loss is expected and too high if it's uncertain or unresolved. So this was an example of Missouri River stuff. So back in 2007, they probed that system. During that probing, what they did was called the spring rise. They were trying to create a natural hydrograph coming out of Gavin's Point Dam out of South Dakota, which was an incredible success/failure. So they did it thinking that sturgeon would respond to this spring rise, and they ended up flooding out some farms, and they've been dealing with lawsuits and that sort of stuff ever since. So I think each week on WebEx we get updated on the Eidecker Farms lawsuit as to what's going on with that and whether or not the DOJ is going to go through the stuff that we've got to bring into court. So it can lead to some issues trying to probe systems like that. Key here is that policies under the two approaches can be different because passive doesn't anticipate learning, whereas active does. Now we have a whole program, I think, in this department about conflict resolution, or talking about human-wildlife conflicts. Now, adaptive resource management is kind of nice because you can start to formally bring folks to the table, stakeholders, and think about conflict resolution in terms of management. Now, this may happen when you've got a state agency. So one of the agencies we worked with is down in Sacramento, working with the folks that were running salmon programs, salmon recoveries down there. There was a lot of angling community that had really strong ways that they thought the fish populations respond to management, which differed than how the state agency thought that the fish populations responded to management. So it's created conflict between the stakeholders. So what we can do, at least with an adaptive resource management context, is we can sit those stakeholders down and see, like, cool. I don't give a shit what your models are. We're just going to put them on the table. We're going to get predictions on them. And we're going to start to learn to see which ones, if there's evidence for one or the other or both. Okay? So, but this can only really happen if stakeholders agree on objectives. If they've got conflicting objectives, it's a whole other can of worms you got to deal with. Then you got to bring in facilitators. You got to start to do a bunch of stuff. So you can't get them to agree on objectives. You're dead in the water. But if you get the stakeholders to the table, come up with objectives that they think are reasonable for the decision problem, but they have different ideas of how the system works and how it responds, you can use adaptive management to try to resolve that by using these posterior probabilities and monitoring. So, like I said, this is really just taking these different ideas from these different stakeholders, incorporating them into the decision model as these alternative models, and monitoring then sort of arbitrates which model is more or less reasonable given the data. Now, a lot of times we run into issues where disagreements on the science is not really about the science. It's not really this your model versus my model. A lot of times we get it that it's just masking a disagreement among objectives. And so that's why we spend a lot of time, at least in the decision theoretic side of the stuff, front-loading objectives, because objectives are key. If you don't have the right objectives, you're dead in the water. So, nice little decision chart here. Think about trying to do adaptive management for conflict resolution. Can you get your stakeholders to agree on the science? Yes? Okay. Do they agree on objectives? No. That means you got to go into some sort of arbitration, some sort of facilitator to come in to help negotiate and compromise so that everybody can get on the same page in terms of objectives. If they agree on the science, agree on the objectives, you just go ahead and do management, okay? There's no need to do adaptive management. Everybody agreed, everybody's on the same page, cool. Go about your merry way. If they don't agree on the science, and they conflict on the objectives, or they don't agree on the objectives, we got conflict, and you're still going to have to bring in somebody to get those objectives put together, or the process may just fall apart, and you have to start over again. But if you get them to agree on their objectives, disagree on the science, we can potentially use adaptive resource management to resolve some of these conflicts using monitoring and explicitly incorporating how they think the system works. So taking their belief on how the science plays out and using it. So that said, it's not a catch-all. There won't work in every situation. You've got to make sure you hit the specific criteria for adaptive management to work. Otherwise, you find yourself in facilitation, arbitration. There's lots of good folks. I think Resolve is one company that have people that will come in and work with stakeholders on objectives, and they will just, you see some of these people work, it's impressive because they'll work a room and just, you get a couple of bullies in the room and facilitators just shut those folks down and move on, but do it in a way that's really, really quite impressive. Okay. So hopefully I've cleared up a lot of misconceptions about adaptive resource management. We've got a program, we've got a process. A lot of the common ones we run into is the fact that people think it's research. I'd argue no, it's management. You're front-loading management and making management decisions and trying to learn from those. Okay? So ARM is first and foremost management. Decisions are made to maximize management objectives. And learning occurs as a byproduct of management in the terms of improving decision making. A lot of people say it's too risky. Everything we do involves risk. Okay? At least when you have a process, you can put that process down on paper so when things do happen that you didn't anticipate, you can try to figure out where they were or what happened to them. We always have risk of over-harvesting a population. We always have a risk of aggregating user groups. And uncertainty increases risk. ARM tries to reduce uncertainty and risk. Okay? So we also have the notion that it extracts from management goals. Absolutely not. We're putting management objectives first and foremost in terms of making the decision. So there's no way that it could distract from management goals. Excuse me. And learning is focused on improving those management so they can meet those goals. All right, this last one, it's probably, if you Snopes it might be a myth or not. It's too complicated and technical. Okay. If you think about most agencies and the elements we've talked about in terms of having an adaptive management program, you've got to have objectives, you've got to have stakeholders, you've got to have decisions, you've got to have monitoring. I would hazard a guess maybe 99.99% of agencies have all that in place already. Fisheries agencies are already going out and monitoring systems. Wildlife folks are monitoring systems. They're collecting wings from birds. They're collecting antlers, jawbones, all that sort of stuff. Now, where it gets to be a challenge is trying to take some of these models that may be black boxing in their minds, making them explicit, where they're explicit, and trying to link those decisions to objectives with models and then targeted monitoring. So kind of taking these elements that are already there and cobble them together. And that might be where some of that myth originates, that it is a little bit technical in terms of how that comes together. But now there's a whole mess of you guys that should be able to put that together, or at least start to, and then figure out who to talk to get it over the end line. Okay, so we've talked about some relatively simple cases of adaptive management. We've gone through some scenarios where we're doing management for robust red horse, or we did some sham examples, and all of those varied in terms of how they treated the utility. Okay? One of the mandates of most efficient wildlife agencies and probably most programs out there is that you should be doing stuff that's sustainable. So if you think about trying to maximize robust red horse from one year to the next, that's probably not the right way to be looking at that. What you're really trying to do is maximize over a 100-year period or something like that, right? So you think about duck hunting, you think about deer hunting, you think about fishing. A lot of those times you're trying to conserve that population so that it can be harvested into the future. And so the processes that I've showed you up to now really haven't incorporated that long-term horizon, that long-term window. So one of the first really successful approaches to this was done for adaptive harvest of American black ducks. And so this has quite a steeped history, and listen to Mike Conroy and those folks talk about it. Really was sort of a shot in the dark. They didn't think it was going to work, but they got some all-stars on the duck team, the working group team. Conroy, Nichols, Hines, all these all-stars of quantitative stuff. But originally, it came down to black ducks have issues. It's an international resource. We got critters that spend time in the U.S., go up to Canada, they're harvested in the U.S. and Canada. Populations have declined from historical levels, but they may be recovering. And there was a lot of controversy over the decline and appropriate management. So this was geared towards overharvest, but there was also a competing hypothesis that it was competition with mallards that was driving some of the declines. And so that had two hypotheses of what was driving the population dynamics and the declines of black ducks. So the reasons for the black duck adaptive harvest management, in this case they just swapped out resource and put harvest in there because they're really looking at a suite of harvest levels, is that they wanted to develop a continental strategy for managing black duck harvest. Well, if you're going to tackle a problem at a continent level using this, that's pretty impressive. So the process should be pretty flexible. And deal with, not necessarily resolve, issues of uncertainty in black duck dynamics, so competition with mallards, issues with harvest, and to make predictive models in monitoring to make optimal, or at least good decisions on harvest and potentially learn. So this is sort of that iterative process. Each year they're going to set what bag limits are, what season length is and stuff like that. That'll in turn affect harvest rate. And they can start to incorporate monitoring to start to learn from that. So being good folks and trying to do a structured decision-making adaptive management program. They had stakeholders, identified a governance structure, so they had the Black Duck AHM group, Black Duck International Harvest Strategy Committee, Canadian Wildlife Service, U.S. Fish and Wildlife Service, USGS. I think there was also different state agencies in there. And they had a governance structure that focused on consensus decisions for objectives. So what objectives were they going to try to meet with this adaptive harvest management program? And different technical issues. Their fundamental objective, at least one of them, was to maximize sustainable harvest. Okay? So if you think about that situation where we're looking at red horse and doing stuff from year to year, it's really going to be hard to evaluate how we maximize sustainable sustainability because we're doing it iteratively over each year. What we really need to be doing is looking at it over 100 years. And they had different penalties, so they got constraints, population goals. So the penalty was applied if harvest went below 500,000 ducks in spring surveys. Parity penalty. So this is getting into the Canada-U.S. relations on ducks. And there was a penalty in their utility, so you guys have been building utilities for parts of your model. There was a utility that if, in some of these decisions, the U.S.-Canada proportions fell outside a range of a 40-60 split, they basically get no value. Okay, so they're trying to maintain that the idea that about 50% of the harvest was going to go on from was going to happen in the United States and Canada. And so basically, a stiff penalty was applied to any country that had harvest greater than 0.6. All right, and we look at the decision context. So the context of this is they're trying to manage black ducks, specifically harvest, to maximize their harvest in the US and Canada. Spatial dimensions, the extent in grain, was looking at the eastern half of North America below. Now, what we haven't seen before is this idea of a planning horizon. That decisions are made annually, but we need to evaluate dynamics over a 100-year time period. That gets at that idea of sustainability. Because otherwise, if you're just trying to maximize black duck harvest, you're not incorporating sustainability. We should go out and harvest them all next year. We meet our objective. Which sounds silly, but if you just see it as black and white and model like that, that's what the optimal decision would be. So you have to build in that sustainability because otherwise you go out and harvest them all. The decision alternatives, looking at season length, bag limits, those are equated into harvest rates. And they're applying this to the eastern half of the U.S. in terms of management zones. In terms of the structural uncertainty, so we've talked about this quite a bit, they used alternative models to represent hypotheses of reproduction and survival process. So they had this reproduction that had competition effect from mallards. They had no competition effect. They had survival, density dependence, with harvest mortality being compensatory versus density independence, where harvest mortality was additive. They went through, did a bunch of statistical and calibrated predictive models to predict the outcomes, so that should sound familiar, predict the outcomes of varying harvest rates. So they're able to take how many ducks are out there right now, run it through the scenario, what's the harvest, given a harvest rate, what's the number that's going to be out there in the next year, on up to year 100. And they're able to retrospectively go back and look at the historical non-harvest survival estimates to start to get at what those were in absence of hunting. And then they were able to take this big, nasty simulation model, and it's really, I don't know, it's kind of anticlimactic when you distill it down to just a matrix. You put together all these moving parts, and it gets distilled down into a policy matrix. They use stochastic dynamic programming to identify the optimal state-dependent harvest policy that maximizes harvest over a 100-year period. So here's, let's see if we can get this all in there. There we go. So that they were coming up with these state-dependent policies. So you got different harvest rates, 0.3. So as the population increases, you can harvest them, have a higher harvest rate. Makes sense. Okay. You get the number of mallards out here driving what the harvest policy is. So we have state-dependent. You go out and do monitoring, figure out how many ducks you got out there, figure out how many mallards you got out there. That's what your policy is for that year. That's how you can set harvest rates, given all this uncertainty, but you're trying to maximize this 100-year time horizon. So, lots and lots of fun, lots and lots of models. Now, I want to get you guys at least a little bit familiar with how this type of optimization works for policy evaluation. Largely because you guys, we don't expose natural resource students to this, and it's probably incredibly important. If you think about trying to maximize harvest, you may be doing something else like trying to minimize an invasive critter. You want to minimize the cost over a 100-year period or something like that, and start to account for structural uncertainty. So I think it has a lot of application for what we do, but I'm suspecting this is the first time you guys have come across this, right? Nobody's played with it before? Okay, good. Okay, so I'm going to step through this example from Appendix E in Conway and Peterson, where we actually take that Anderson 1975 model, and we're going to develop the ideas or optimal policies for maximizing harvest, given some of the stuff that Anderson talked about there. So let's see. Let me go back up here and jump into that paper real quick. Show you guys what he did. So he came up in 1975 with starting to develop models for ducks and starting to look at the environment and the animal. And the gist was that he was basically taking a simple population model where he's got the number in the next year plus the number in the previous year plus the young, basically projecting that out over time, linking that to the number of ponds on the landscape, so accounting for these sort of state-dependent things that you can monitor. So if you were going to set a harvest for that year, you go out and count how many ponds, or estimate how many ponds are on the landscape, estimate how many ducks are on the landscape, and that would dictate what your harvest rate should be, given some of these factors. So predicts the number young of the year from the number of ponds and the number of adults out there, develops these predictive relationships, strings it all together, we get some alternative relationships, does a pretty good job calibrating the model, looking for pond dynamics, estimates the fall population, given a bunch of survival, and so pins that together, adds exploitation, and all that jazz. And he accounts for the fact of harvest rate might be a little different whether or not you've got additive versus compensatory mortality. So, lots of moving parts, lots of neat stuff. And it's a pretty good example to run through how we actually go through and do what they did on the black duck adaptive harvest plan and see it on a little bit smaller scale as to how the underlying process works for doing this. Okay, so jump into R here. So the thing that I'm going to need to do this is a library called MVP Toolbox, which does that, what's called stochastic dynamic programming. It calls it policy iteration. But I can call that up. Okay, it's going to be grumpy at me because some of these packages are a little bit old. But I can basically give it a bunch of decisions. So in this case, we've got different harvest decisions. We can harvest at a rate of 0.1, 0.2, 0.3, 5, 10, 15. Okay, so this is a really simple example before we jump into the Anderson model. So this would basically be saying, I want to figure out what's the optimal decision if I've got 5 million, 10 million, or 15 million critters out on the landscape. But I want to do it in a way that's sustainable. So what this thing's going to require is it's going to require some transition matrices. We're going to have 1, 2, 3 matrices, and these are going to correspond to the 3 decisions, and each row corresponds to the states, the abundances. Now, we can deal with model uncertainty using these priors. So suppose we've got a model that represents something, additive, compensatory, something like that. We got a prior probability on that of 0.5. And basically what we can do is that we can take our transition matrices here, under these different models. So suppose under model 1 I get a transition matrix that looks like this. These should all look familiar from your conditional probability tables in your models. You guys have probably seen enough of those probabilities by now, right? So we know that this represents the probability of going from 5 to 5, 5 to 10, 5 to 15, and so on. But it's for a harvest rate of 0.1. Okay? So what we can do now is we can count for the structural uncertainty, so the uncertainty in the two models there, by simply averaging, taking the weighted average of those transition matrices and plug them into that array P. So now if I go and look at P, P1, it's got this new transition matrix that represents the weighted average of those two from before. We do the same thing down here for harvest rate is 0.2. And we're starting to cobble together this P matrix that represents, given a harvest rate of 0.1, these are the probabilities of going from 5 to 5, 5 to 10, and so on. We go down to 2, that's a harvest rate of 0.2. We see 0.6, 0.31. Makes sense if you're going to harvest a population a lot harder. Probably more likely going to stay at its current state or drop down. We go down and do the same thing for matrix 3. So this is the decision of 0.3. We take the weights, figure out the transition matrix. So now we've got this array. So array is just a bunch of matrices where we've got the transition probabilities for each state given a different harvest rate. Now we need to link that to a utility that we can maximize over the long term. And that's simply, in this case, we could do harvest. So this rewards matrix represents the harvest. So harvest rate, when you got 5 times 0.1 equals 0.5, and so on. Okay, so that's the amount of critters that would be harvested in an annual cycle. All right, and here's where the magic happens. There's a tool called MVP policy iteration, which basically takes those matrices and runs them backwards, so starting at year 100, runs them backwards until it finds a stationary policy. Now, I don't expect you guys to go into it and figure out how to do that. It's really difficult. But it does it for you. So you can basically guarantee the optimal decision for this reward matrix and those transition probabilities. And all we do here is hit run. Apparently it doesn't want to. Okay. Change my discount a little bit. And so what it does is it runs it over a long time horizon. So in this case, MVP policy defaults to 1,000 iterations, which would be 1,000 years, but it reports values as 100. So this would be the harvest value over 100 years. And these are the different policies that were selected. So decision 1, 3, and 3. We can use that to make a policy table if we wanted to. If I look at it, it's basically like a lookup table now. So if I go out there and I've got 5 million critters on the landscape, the optimal harvest rate is 0.1 if I want to sustain harvest 100 years into the future, and given the structural uncertainty of having those two hypotheses contributing to the transition matrix. If I've got 10, we can harvest at 0.3, and 15, I can harvest at 0.3. So it's a way to figure out what the optimal decision is given these long-term dynamics. So, not super exciting on that one. Here we're going to get into and look at that Anderson model. So in the Anderson model, they had ducks ranging from 1 to 15 million. Harvest rates can be evaluated from 0 to 0.4. We're going to look at it in increments of 0.1. You could totally break it out and do like increments of 0.01, but it would be computationally intensive. And in a lot of cases, managers don't care if you tell them a harvest rate of 0.12 or 0.15. They're probably about the same, right? So usually if you work in whole numbers, it works out better for communicating with managers. In a lot of cases, it doesn't matter too much. So now we're taking the bits of the Anderson model. So I've got this data frame where I've got different combinations of initial population abundance. So in millions of ducks, 1, 2, 3, 4, 5 million up to 15. I'm just going to do it for one pond scenario. So we've got 2 million ponds in the landscape right now. We've got harvest rates that go from 0 to 0.4. And because we need to do some stochastic replications, I've got 5,000 replicates for each one of the combinations of initial population size, pond number, and harvest rate. So here, this is the model on Anderson that predicts the number of young recruiting as a function of ponds and the number of ducks on the landscape. Gives us a deterministic prediction. So if I look at it'll give us the same number given 1 if we go down to the different harvest rate. We put some noise on that. In this case, we're going to pull it from a truncated normal distribution so that we're adding a little bit of noise. The variance is going to scale with the number of young out there, and it's going to be constrained to be 1 or greater. So that now these things have modified a little bit, so we're accounting for statistical uncertainty on that. Now, if we want to calculate how many ducks are out there in the fall, simply the survival rate that he had in the paper times the number of adults out there plus this new number of young that have hatched and recruited to the population. Now we need to figure out how much harvest occurred out there. And so it's simply number of critters out there in the fall times number of harvest rate times the number out there in the fall, and so on. And so basically multiplying how many ducks are out there by the harvest rate to give us how many animals were harvested. Here we plug in from Anderson's paper what the expected survivals are given additive mortality for adults and young. And we can calculate what the number of adults would be given that one hypothesis. So down here we're just multiplying the number times the survival plus the young times the survival. Okay? Simple enough, just like balancing your checkbook. You got numbers out there, you harvest some survive, and you're just keeping track of them. Down here we're doing the same thing except for Anderson had put together a compensatory mortality model for youngs and adults. So this is that alternative hypothesis. And and we can figure out how many are going to be out there if we have compensatory mortality going on, given the good science that Dave Anderson did. Now, one of the keys on this SDP that becomes a little problematic is that we have to have square matrices. So if we've got 1 through 15 million ducks out in the landscape, they can't transition into new states. So sometimes you might harvest, it might go below 1, so it'd be state from 0 to 1. Basically, all we have to do is bin those into the state before, so that we can have 1, 2, 3, up to 15. And that's all this little bit of code is keeping these new states from arising, so that we can have a square matrix. I'm using the floor function in here, because basically floor just makes it an integer. So if I have a 1.23, it gives me a 1. You're basically getting anything that's between 1 and 2 makes it a 1, 2 to 3 makes it a 2, and so on. So it's just like discretizing, but a little bit quicker, and we don't have to use the cut function. So now I need to come up with what the transition matrices are. So we've taken the initial population of ducks on the landscape. We've got 2 million ponds on the landscape. We've got different harvest rates. We've got a little bit of structural uncertainty in terms of additive and compensatory. We're going to make a table that's going to calculate up the frequencies. And so in this case, this is going to return an array where we're going to have a number for each combo. So we're going to have a matrix of initial populations, future populations, and each matrix is going to represent a harvest rate. So if I look at that, so these are basically all those frequencies that you can use to calculate the transition probabilities. So probability of going, or out of those 5,000, 4,917 kept in 1, 83 went from 1 to 2. Okay? So this should all look pretty familiar relative to what you guys have been up to in making conditional probability tables. We turn those into real transition matrices so that the rows sum to 1. We go here, so 99% of the time, 1's going to go to 1. There's a small chance it's going to go from 1 to 2. Okay? So basically accounting for the fact that we've got 2 arrays, one for additive harvest, one for compensatory response, and we're accounting for the initial stage of the population, whether it's 1 million ducks in the landscape, up to 5 million ducks in the landscape, and we're assuming right now that there's 2 million ducks on the landscape. Okay. Now we need to figure out what the value of those are that we're trying to maximize over. So in this case, we're maximizing over harvest. All I need to do is figure out a matrix that gives me a harvest value for each one of those states given a decision. So we're going to have a matrix that's 15 rows representing each one of the abundant states. So 1 million, 2 million, 3 million, 4 million, and each one of our harvest rates. So if we have a harvest rate of 0, the value of that is 0 because you're not harvesting anything. Harvest rate of 0.1 ends up being about 0.27, 0.55, 0.83, and 1.1. Okay. Make sense to folks? It's really not too difficult. You're basically taking a really complicated model and distilling it down to some transition matrices. Now we can go back and do these probabilities. So if we're starting out, we don't know whether or not it's 0.5, 0.5, 0.6, 40, 70, 30, whatever. If we don't know if additive or compensatory mortality is occurring, we can do 50-50. And we can weight those transition matrices by the priors and make up a new transition matrix that basically gives 50-50 weight to additive and compensatory. And we get these new transition matrices that are the weighted average of those two. here where the magic happens. We're just going to use this MVP policy iteration. We're going to take that transition matrix that I have. So it should be what we had, four decisions. This one should be 4 matrices with a 15 by 15. Okay, we got 15 rows, 15 columns. And this is for decision for harvest rate of 0.4, 0.3, 0.2, 0.1, and then a harvest rate of 0. So, okay. Let's see who the winners are. So now this, unlike before where we do these sort of single point in times, this thing's going to figure out what is the policy that maximizes harvest over a long-term window so that we're doing sustainability. It runs. All I did here is you run a small discount so that you're discounting population into the future. I did seed it with an initial policy, which was basically I said harvest at the maximum rate, so 0.4 initially, and then it would basically iterate from those. I gave it some starting policies to iterate from. Usually the best is to start with the worst case scenario, so just give it the highest harvest rate. And so that's a vector of 15, represents each one of the population abundances. I gave it a max iter of 100. If I look at the output on that, gives me harvest for each one of the initial abundances, and it gives me a policy, optimal policy. So remember I had four decisions, so 0, 0.1, 0.2, 0.3. Each one of those represents one of those policies.
So that's saying the first two years your best not to harvest anything?
No, it's saying that if you've got 1 million ducks on the landscape, you don't harvest.
Oh, okay.
You got 2 million ducks on the landscape, no harvest. You got 3 million ducks, you're going to harvest at 0.1. And so, good question, because that sets up, we can make a policy table, just like we did before. So we've got these initial abundances. We've got our harvest rate, HT, is indexed by the policy. So we put that together. It gives us a lookup table, essentially, that a manager can say, I've gone out and monitored, found that there's 1 million ducks on the landscape. We can't harvest this year. We've got 2 million ducks on the landscape. We can't harvest this year. 3 million ducks on the landscape. We can have a harvest rate of 0.1. And it goes up until we get to a 0.3. Make sense? And in no place did we get to the point where we could harvest 0.4. So now remember, we had a 50-50 split on whether or not we had additive versus compensatory mortality going on. So what should happen if you say learn that compensatory is really what's driving the show? What should your policies do? You should be able to harvest them a lot harder, right? So let's see if that happens. So here, because I've got all those transition matrices set up first, I'm just going to throw and say, we got about a quarter of the weight going to additive mortality, which means that 0.75 is going to compensatory. We recalculate that transition matrix using these new priors. So maybe this is updated by Bayes' rule because we had some monitoring data and we're able to do it that way. We rerun that same code. I'm going to add that to the policy table. And all of a sudden we're seeing that now we can harvest this guy. Well, we got 3 million ducks on the landscape, we can harvest that guy a little bit more. Now we're seeing a transition. Once we get 10 million ducks on the landscape and we start to learn that compensatory mortality is going on, we can increase the harvest rate and provide more hunting opportunities.
This is taking into account kind of like the length of a season, of the hunting season.
Mhm.
I mean, because
Yeah, you
I know
basically
we're dealing with rates, but
Yeah,
it's,
so it does become a challenge in terms of how do you equate a 0.4 to a hunting season and a bag hunted.
Sure.
And so where you got people who are reporting what they catch or what they harvest and that sort of stuff, you can start to correlate that to a harvest rate. And then the thing that we won't get into this class, but that you can put in here, is the idea of partial controllability. So if you do impose a 0.3 harvest rate, what's the probability you're actually going to reach it? So a lot of times you may exceed it in a harvest situation, which is bad, and so you can actually account for that. But I like to think about it in terms of invasive species. So we're doing some carp work where we set up some target harvests that commercial fishermen were going to try to hit. So they had to remove a certain amount of biomass from the system. But the probability that they were actually going to get that biomass was it was uncertain. They might get 50% of it, 25% of the time. 75% of that limit, that might be 75% of the time. And so you can account for that partial controllability in these types of models, but it gets a little bit more complex.
I'm sorry.
No, that's fine. Good questions.
Does it account for like the amount of hunters? Say next year, twice the amount of people sign up to go hunting, and
No.
we reach the 0.3 in half the time.
Nope, it doesn't. So that would be something you could build into your underlying model. So you'd probably want to build, at that point, a more dynamic harvest model so that you could link it to expected effort or something like that, as opposed to some sort of harvest rate. So be able to map expected amount of days that a hunter is going to be out with how much they're going to harvest and that sort of stuff. And so that adds more complexity to it, but it's not out of the realm of possibility, because really all you're doing is adding that into those models. So as opposed to multiplying by a harvest mortality, all of a sudden you're going to run scenarios of like, if we've got this many duck stamps sold, that maps to this amount of harvest. Good question. So hopefully that will trigger some creative juices on you guys in terms of thinking about a lot of stuff we do does involve long-term sequential decisions. So thinking about the basic species management. So going back to that carp example, when I have like a week, I want to do this for common carp in a lake, where I can start to look at what's the optimal policy for removals to try to minimize biomass over a 100-year period, that sort of stuff. Probably has some pretty good applications to other stuff going on in terms of basic species removals, so zebra mussels, plants on the landscape, pigs, whatever, where you're putting a big amount of effort in doing annual management actions, trying to figure out what those policies are, trying to minimize biomass, minimize numbers over the long term. So that's just a matter of taking that harvest number, swapping that out for abundance, making it negative, and then you try to maximize it. So, anyways, well, that's all we got time for today. So if you guys have any questions, next Wednesday will be our last class. We'll finish up with expert elicitation, go over those numbers that you guys put together class. And also up here, if you guys want to look at it, or not, I'll probably try to post a link to it, is in this book someplace they have like this Cosmo quiz for adaptive management. You can kind of go through and answer yes, no, maybe. And then it'll say, yes, you qualify for adaptive management. So, kind of neat book that the DOI put out.